We're at the MC Machinery HQ here in Chicago, Illinois, and we're going to learn about everything that the AZ600 is bringing to the additive manufacturing world. John, what's this machine doing behind us?
This is a 3D metal printer, and it is printing parts out of metal.
So, is this a machine that's using powder, or how is it printing the metal?
This is using a wire, no flux, no coating, just a pure metal wire. It's being run underneath a near infrared laser, approximately 3 millimeter beam. It's coming downwards. The wire comes in on a 45-degree angle, melts, creates a melt pool, and then the head or the axis, it's a 5-axis, so depending how you programmed it, that melt pool will follow a path with the solid model that you've created. Create a step file, import it into the CAM software. You create a NC software that you put into the machine, and you print metal.
And what's the major difference? I'm more familiar with the powder. What's the biggest difference between wire and powder when it comes to printing metal?
Powder is got to be handled carefully. There's explosion, fire hazards, there's respiratory issues, cleaning issues, disposal issues, recycling issues. The wire is very clean. It's changing from one wire to another is a 5 to 10 minute process. Disposal and recycling is simple. There's a small tray in the bottom, and it's much safer to handle. You don't have to put a hazmat suit on. You can just, I could change the wire if I want to do some cladding. 10 minutes later, you're cladding.
So in something like that, I know on the powder side, one of the big concerns and limitations is porosity in the prints that they're making, and the applications are kind of limited. Does wire have that same struggle?
Every piece of metal you see has some porosity in it. We're printing under 8,000ths of an inch. It's very tiny, and that would be like at a maximum size. Powdered metal tends to have some voids and needs some hot isostatic pressing or hip heat treatment to cure that. This type of technology you can't cure. If there is any voids, it's usually your slice path. Once you've designed a good part, it's pretty solid. Porosity is very low, and there's no extra heat treating to fix the part.
What industries do you see this machine being the best benefit to?
I think if you're forging repairs, mold repairs, low volume exotic alloys that you would, in times of past, you might make 50 parts of, let's say, a nickel Inconel at a forging house, and they more ideal to probably print that today. Especially if you don't have tooling, because the tooling is digital. So I think there's a big future in that. Also, if your company has parts, let's say your company's been in business 50 years, there might be, maybe you want to take care of a customer as a 40-year-old machine and there's nothing left tooling-wise, there's no spare parts. You could at least print and machine something and satisfy, like one-offs, two-offs, or maybe you make an impeller and each job has a different flow rate. Might be different impellers, so you don't need one. You need 50 different kinds when you need them, and that's what 3D printing will give you.
That sounds really interesting, especially when you're talking about a complex shape like an impeller or something like that. Historically in manufacturing, you want the strength, so you're going to machine that from solid, and that takes a long time to do.
We're building about 0.5 millimeter oversized, but you can adjust it. But when you run our CAM software, which is proprietary, it'll overbuild everything automatically, but you can scale up or down. But it's generally just enough material that you can machine it off and get a good part when you're done.
So we're reducing machining time, we're reducing waste, with a lot of people out there want to reduce their waste. I'm curious about any other uses for this printer out in the market.
I mean, that's pretty much going to kind of evolve organically, because the direct energy deposition machine we have is fairly new in the market. There's many powder bed metal and powder bed fusion. There's a lot of different types of heat sources. There's a lot of varieties right now, and using a laser DED with the 5-axis will find its home somewhere in the industry. It's not going to make accurate parts. Remember, it's like a casting. You're going to be machining post-processing. There's going to be wire EDMs, probably sinker EDMs or CNC mills involved in the process. You can trade off easily. You can use palletization and go from one machine to another. So you could print part of a part, pass it off to the CNC, have some work done, bring it back into the printer, print more, or do a cladding. Maybe change materials, make a high wear area, a harder material like a cobalt, like a Stellite 6. We've done that on some parts.
That to me is really interesting, because I mean, it's technically possible right now for some shops out there where they have a welder that's skilled enough to do that cladding process. But I've met a lot of welders, and probably only a handful of them could actually properly clad and get that bond quite right between the mixed metals. When you start mixing them, there's a lot of science to it and a fine hand. So how is the quality of the cladding and the welding that this machine's able to do?
Well, one of the benefits of having a machine do a weld or the cladding is consistency. There's human error that, there's great welders out there that can do it by hand, but the machine's going to repeat consistently, and you're going to get the same results. You can fix your machine if you have numerous parts and just set the part up and have it busted out and just keep rotating the parts in. It's definitely a more exact science, but I'm not trying to down a human welder, but machines do a fine job.
John, is there anything else you think that people out there should know about this machine?
So one of the things is, if you're a manufacturing company and there's a pretty significant expense in building tooling for whatever process it might be. So let's say even investment casting, you still need to make tooling for the wax mold and whatnot. Here it's digital, so you don't have to wait to get the tooling made. Could be 18 weeks, 14 weeks. What if there's a mistake in the tooling? You got to send it back to the shop. So there's generally a pretty long lead time before your tool's done, a heavy expense, and then you got to run the tool. You got to pay for a setup. You got to, it's expensive unless you're making 10,000 parts. But if you're making like more of a low volume, you need 50 parts, 1 part, 20 parts, 100 parts. You could create your tooling digitally. You could print those parts, that file, once all the processing conditions are set in and it makes a good part, it'll always make that part. So you kind of build a library of tooling, but it's on a disk. And it's the future. It really is.